Today I'd like to talk about regression inference. So please open up your study guide to this particular section. Now let's begin with the regression model example. Now how much would an adult female weigh if she were 5 feet tall? She could weigh varying amounts. In other words, there is a distribution of weights for adult females who are 5 feet tall. This distribution is normally distributed, we hope. So as long as we have a large enough distribution, we're going to assume that weights will be normally distributed. What would we expect for other heights? And once again, for other heights, we would expect that these distributions as well would be normal. So where would you expect the true least squares regression line to be if we were to associate height versus weight? Now, since we are expecting normal distributions for each one of these heights, we're going to expect our least squares regression line to be at the means of all these normal distributions. So, our least squares regression line can be represented by the model mu sub y equals alpha plus beta x, where alpha represents the y-intercept of our least squares regression line and beta represents the slope. Now what about the standard deviations of all these normal distributions? We would want the standard deviations of all these normal distributions to be approximately the same. Now this leads us to our regression model. Now the mean response mu sub y has a straight line relationship with x such that mu sub y equals alpha plus beta x. This is our least squares regression model from the population of all values of our bivariate data, where the slope beta and the intercept alpha are both unknown parameters. Now for any fixed value of x, the response y varies according to a normal distribution. Repeated responses of y are independent of each other. And the standard deviation of y, which we'll call sigma sub y, is the same for all values of x. Sigma sub y is also an unknown parameter. Now we use the model y hat equals a plus bx to estimate the population least squares regression line mu sub y equals alpha plus beta x. The slope b of the least squares regression line, based on our sample data, is an unbiased estimator of the true slope beta. So if we were to take all possible samples of a particular size and create all the possible least squares regression line based on the sample sizes with that bivariate data, the average of the slopes would be equal to beta, our true population parameter for the slope of our least squares regression line. Likewise, the intercept A of the least squares regression line is also an unbiased estimator of the true intercept alpha. A and B are both unbiased estimators of our least squares regression model. Creating least squares regression lines from a particular sample and continuing to do it over and over until we've taken all possible samples of that particular size would lead us to several different least squares regression line models. And the average of all the slopes and the average of all the y-intercepts will lead to the true parameter value of alpha and beta. Now the standard error S is also an unbiased estimator of the true standard deviation of y. And the formula for the standard deviation of our least squares regression line model can be found by taking the square root of the sum of the squared residuals divided by n minus 2. Notice when we divide by n minus 2, we're basing this on the degrees of freedom for this particular model. The degrees of freedom is equal to n minus 2 since we lose 2 degrees of freedom for estimating both parameters alpha and beta. So when we estimate more than one parameter, we're going to lose an additional degree of freedom. Therefore, the denominator here is going to be n minus 2. Now let's talk about the sampling distribution for beta. Now suppose we took